Yesterday we finished up the lab on the speed of sound, experimentally determining it, and we found out that air at 0 degrees Celsius allows sound to travel at 331.5, 331.0 meters per second. And we also learned that as the temperature changes, the speed of sound changes because it's a mechanical wave. So let's take a look at the speed of sound in a variety of other materials and different temperatures. So air at 20 degrees, it moves a little bit faster. 343 meters per second is the temperature and the speed that we're going to use for most of our speed of sound in air problems. Sometimes we'll use 345, but for the most part, if it doesn't give it to you, you're going to use this value, 343 meters per second, as our average room temperature speed of sound in air. Helium is a lighter gas than air. Remember, air is made up mostly of nitrogen. 80% of it's nitrogen, about 20% of it's hydrogen, a little bit of water vapor, a little bit of a variety of other gases thrown in. So it's more dense. Helium, even though it's less dense, the particles move faster at a given temperature. And so actually sound can travel more quickly in helium. If you've ever inhaled a helium balloon, you know that when you talk, your voice sounds much higher and squeakier because it's not only changing the speed of sound, it's also changing the frequency at which your vocal cords vibrate. They vibrate at a higher frequency, giving your voice a higher pitched sound. Sound travels a lot faster in water. In fresh water at 0 degrees C, it travels about 1,400 meters. Warm up the water and it travels faster. So fresh water at roughly room temperature, 20 degrees Celsius, sound is going to travel at about 1482 or almost 1,500 meters per second. So almost 100 meters per second faster in the warmer water. If I look at seawater, sound travels even faster in seawater. And if we stop and think about that a little bit, hopefully it'll make sense. Seawater has salt and a variety of other minerals added in, on top of which has got a lot more little microorganisms, microscopic sized more organisms living in it that make it more dense. More dense, faster sound speed. Now we move into solids. Steel is a fairly high elasticity material, so sound is going to travel because A, it's dense, and B, it's elastic. Speed of sound is very high, 5941 meters per second. That's almost 6 kilometers per second. That's moving right along. That's why train robbers learned that they could stick their ear to the train rail and hear sound of the approaching train way before they could hear it if they're just standing and listening through the air normally. It turns out that granite allows sound to travel just about as quickly. So about 6,000 meters per second, about 6 kilometers per second is how fast sound will travel in granite. Let's take a look at some characteristics of sound waves. First of all, let's talk about frequency. Frequency is a numerical value. It's the number of waves per second that a sound wave travels. Frequency is the technical name. Pitch is more of a perception. So pitch, when you're talking about it either in musical terms, vocal music or instrumental music, when you talk about pitch, what you're referring to is your interpretation of a numerical value of the frequency. So we'll put pitch up here. Again, pitch is a subjective interpretation of frequency. It doesn't refer to necessarily a specific numerical value. Humans can hear a wide range of frequencies. If your hearing is really good, you haven't damaged it by having your music turned up way too loud with your headphones, your earbuds in, you can hear from about 16 hertz up to about 20,000 hertz. Frequencies greater than 20,000 hertz are called ultrasonic. Many animals can hear frequencies above 20,000 hertz. Dogs, bats, for two, can hear sounds much more highly pitched than what people can hear. If I have sounds frequencies less than 16 hertz, this is called infrasonic. Turns out just because you age, you also lose hearing of frequencies at various ends. You tend to lose the higher pitch frequencies first, the older you get. The structures in your ear just start breaking down over time as you age. Detectors that process the high frequency are the ones that get damaged and traumatized the most, and so they're the ones that fail first. Let's take a look at a chart that relates sound frequency to sound intensity or loudness. So here we have intensity and something called relative intensity. And the units for that are decibels. We'll get to that shortly. And this is relative loudness. As the numbers get bigger, things get louder. Along the bottom, we have frequency. And so we have low frequency on the left, and we have high frequency on the right. And this range is essentially the range of human hearing. So one thing that you might take a look at is when I have really loud sounds, I have something called the threshold of pain. And if you've ever been around really loud sounds, sometimes they're loud enough that it really makes your ears hurt. If you've been to a concert and sat up near the front, you may find that as you leave the concert or the next day, your ears are ringing. Okay, that's due to the very high intensity of the sound waves pounding on your ears. And so when I have low frequency, the threshold of pain is fairly high. Frequencies that are more in the middle range, so right here, middle being 2,000 to 5,000 hertz, are not quite as high. What that means is the higher frequency, you don't need it to be as loud for it to hurt. And then it works its way back up in the high frequency range. In the middle, we have our region of speech. If you think about the range that your voice can go when you're talking, it goes from about 100 hertz. If you're a male, their voices tend to be deeper, lower frequency. Females and children tend to have higher frequency voices, and so their range then is everything in between. Yours may not extend as far. Music region, this includes singing. This can also include music region instruments. So you can generally sing in about the range that you can speak. Sometimes you can extend your range a little bit when you're singing. Musical instruments, though, can play lower frequencies than we can create with our voices. Musical instruments can also create higher frequencies than we can with our voices. The other end of the spectrum, threshold of pain being the top, is threshold of hearing. When a sound is so soft that we can't perceive it, then we're looking at the threshold of hearing. Again, we can hear really, really soft sounds between about 2,000 and 5,000 hertz. That's about where our threshold of pain is also the lowest. As sounds get lower in frequency, it gets harder and harder to hear them. And so when I'm down near the lowest end of my frequency range hearing, I need to have a really loud sound to be able to hear it. High frequency goes up as well, but not nearly as quickly. So things that are outside this range are sounds that we can't hear. They're either too soft if they're down here, or they are too low frequency if they're down here, or too high frequency if they're up here. Most sounds in between we can hear. Okay, that graph showed us intensity. Let's take a look at intensity or loudness. The symbol we're going to use for intensity is a capital I, and intensity is proportional to amplitude of the wave. It's proportional to amplitude squared. We also learned earlier in the last unit that energy is proportional to amplitude squared. So energy and intensity are very much related. So A is amplitude, and the equation actually that relates them eventually is intensity is equal to power divided by surface area. Sound waves travel in 3 dimensions, so we can think of a wavefront of a sound wave as a sphere. So as this wavefront, this spherical surface, travels away from the source, it gets larger and larger. And so the surface area that we are taking a look at in our intensity equation is the surface area of a sphere. And the surface area of a sphere is 4 pi r squared. So our intensity equation is power over area. Units for power are watts. Units for surface area are meters squared. So intensity units are watts per meter squared. And as we saw on the chart on the previous slide, the lowest intensity we're going to call I0, and this is called the threshold. The threshold intensity is the minimum intensity that human ears on average can detect. What we saw also on that previous chart is the threshold intensity depends on the frequency. The other thing that the chart showed us is there's a specific value for the threshold intensity, and it's 1.0 times 10 to the negative 12 watts per meter squared. Okay, this is a number that we'll be using, and so that's a number that you might want to jot down and have available. This equation is also an equation that we're going to be using very shortly, and so you might want to make sure that you know it. And if you forgot the surface area of a sphere equation, there, you've got all three of them right on this page, so you might want to make sure that you have them jotted down somewhere.